Okay, let's take a look at the review for test 2. Question 1 is asking us to determine the quartiles for the given data set. The data set has 15 values, which is odd, and that points us to the n plus 1 over 2 position. So 15 plus 1 over 2, 16 over 2, or the 8th position. So let's find the data value that lives in the 8th position. 1, 2, 3, 4, 5, 6, 7, 8. 22 is quartile 2. Now we'll find the median of the lower half. So we have 1, 2, 3, 4, 5, 6, 7. Again, 7 is odd. 7 plus 1 is 8. 8 divided by 2. So we're looking at the 4th position. 1, 2, 3, 4. So 19 is quartile 1. And then the median of the upper half, we're going to do the same thing. So we'll see 27 is quartile 3. And then part B is asking us to find the interquartile range, the lower fence, and the upper fence. Remember, this is for outliers. So the interquartile range is, remember, Q3 minus Q1. This is from your tables and formulas. The interquartile range is Q3 minus Q1. 27 minus 19 gives us 8, and then the lower fence is Q1 minus 1.5 times the interquartile range, which we got in step 1, which is 8. So we get 7 for the lower fence, and the upper fence is 39. Quartile 3 plus 1.5 times the interquartile range. So let's locate the lower fence and the upper fence. 7 and 39. And then remember, anything less than the lower fence or more than the upper fence, we're going to call an outlier. So let's check the first one. We do have, okay, so outlier. We do have 1 based on the lower fence, which is 3. And the upper fence, we don't have any on the upper fence. So the only outlier that we have in this data set is 3. Okay, next question. Says the average score of local students on a college entrance exam is 110 with a standard deviation of 5. So let's go ahead and label the empirical rule. The mean is in the center. And then the mean plus 1 standard deviation is 115, 120, and 125. 105, 195. Part A says about 65% of college entrance exam scores will be between what two scores? Well, we know that 68% is within 1 standard deviation of the mean on both sides. So 68 is really, really, really close to 65. So we can say that about 65% of college entrance exam scores will be between 105 and 115. And then part B says what percentage of students, find the percentage of local students with scores above 125 or below 95. Okay, so let's label the curve again. 110, 115, and we'll locate our boundary point, 95 and 125. So the percent below 95 is 0.15%, and the percent above 125 is 0.15%. So we get 0.30%. Okay, let's take a look at next question here. So this time we've got a question that involves the idea of z-scores. It says suppose that the mean height for all women in the world is given by 63.6 inches and the standard deviation is given by 2.5 inches. Further, suppose the mean height of all men in the world is given by mu equals 75 inches and the standard deviation is given by 3.0 inches. Use the z-score computations to determine which is more unusual. A woman who is 59.85 inches tall, or a man that is only 67.5 inches tall. So remember the z-score formula, and here we're probably going to be dealing with a sample. So is x minus x bar over standard deviation. So at this point we just have to plug in the individual height for the male minus the mean divided by the standard deviation, and then also for the female. So on the male side, we get 67.5 minus 75 divided by 3 gives us minus 2.5. And then the woman is 59.85 minus 63.6 divided by 2.5 gives us minus 1.5. So both of these individuals are below the average. But which is more unusual? Well, the man would be more unusual, okay? Because he is further away from the average. But remember, if I was to change the question and ask who is relatively taller, then the female would be relatively taller in this case because she is closer to the average on the negative side. And we know that if we start off way on the negative side and then approach the average, then the person gets taller. So the female is relatively taller, but the man is more unusual. Okay, next question says identify the sample space of the probability experiment, tossing 3 coins and recording the sequence of heads and tails. Okay, so remember, you want to use a tree diagram here. So you want to ask what can happen on the first toss of the coin. Well, we can get heads or tails. And the second toss, we can get heads or tails. And then the third toss, we can get heads or tails here, heads or tails here, tails, heads, tails, heads, tails. Okay, so remember to read the tree, you basically just want to think about reading heads, 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 and then you go heads, heads, tails. Okay, and that branch is completed. And so next we'll go heads, tails, heads, and then heads, tails, tails, and that branch. And then you just move on. Tails, heads, heads, tails, heads, tails, and then that branch is done. Tails, tails, heads, and tails, tails, tails. Okay, and you'll see that I have listed out every single possible occurrence of tossing a coin 3 times and observing the sequence of heads and tails. So now the question part A says, what is the probability of obtaining exactly 2 tails? Well, let's go back and look at them. So exactly 2 tails, that's going to be this one. Oh, I'm sorry. I'm counting heads. Exactly 2 tails would be this one, and this one, and this one. So we see the probability is 3 out of the total number of outcomes in the sample space, which is 8, so the probability is 3 out of 8. What's the probability of obtaining exactly 3 heads? Well, that can only happen in one way, and that occurs right here. So the probability is going to be 1 out of 8 of getting exactly 3 heads. Okay, now we'll move on to the next part. What is the probability that you will roll a fair 6-sided die and get a number that is strictly less than 4? Okay, so the first thing we want to think about is when we talk about a fair 6-sided die, we actually mean just a dice that has 6 sides. So the sample space is going to be 1, 2, 3, 4, 5, 6. Okay, now strictly less than 4, that means that the number x must be strictly less than 4. Strictly means less than 4, not equal to 4. And so the event space is going to be 1, 2, or 3. And that's what we have here. We have the event space is 1, 2, or 3. So now what's the probability of E? Well, the event E can happen in 3 ways. 1, 2, 3 divided by the total number of possible outcomes. 1, 2. So the probability is 3 over 6. Or 1/2. Now, if we were to roll a fair 6-sided die 1,000 times in a row, what is the best estimate for the number of rolls in which you would obtain a number strictly less than 4? Well, that would just be 1,000 times 0.5 or 500. And then part C, would it be unusual to get a number that is strictly less than 4? And we'll go by the book's definition here. And remember, the book just says that anytime an event is less than or equal to 5%, it's unusual. Well, the probability of the event that we got above here, probability of the event, is actually 1/2. So that's definitely not less than 5%. So we would say no, it is not unusual. Okay, next question. Suppose we draw a card from the top of a sufficiently shuffled deck of 52 cards. What is the probability that you will draw either a face card or a 10? Now remember, these two events, a face card and a 10, are disjoint. Okay, and so that means we're going to use the addition rule for disjoint, which says the probability of A or B is equal to the probability of A plus the probability of B. So this is going to be the probability of a face card or a 10 is equal to the probability of a face card. Well, how many face cards are there? Well, there are 12 face cards. Remember, we're only including the jack, the queen, or the king as a face card. So that probability is going to be 12 out of 52. And then the probability of a 10, well, there are 4 10s in the deck, so the probability would be 4 out of 52. So that gives us 16 out of 52 here. Okay, now we're going to contrast this to part B. What's the probability that you will draw either a black card or a jack? Well, these two events, a black card or a jack, are non-disjoint. Okay, and remember the rule for this says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So let's set the question up by finding the probability of a black card or a jack. And then the probability of a black card, we have 26 of those. So 26 out of 52. the probability of a jack. We have 4 jacks. Okay, so the probability of a jack is 4 out of 52. And then minus the intersection of the black cards and the jacks, which would actually be black jacks. So how many of those do we have? We have 2 of those, so that's going to be this probability here. So 26 plus 4 minus 2 gives us 28 over 52. Okay, next question. Okay, this question lists out the frequency of use for a customer and how the customer rates the shipping company. Okay, and so we have the rating across the top, high, medium, low, and then we have the frequency of use down across this first column here. So the question is, what is the probability that a randomly selected respondent did have a high level of satisfaction or use the company more than 5 times per month? So remember, what you basically want to do here is just kind of circle high level and then more than 5 times per month. Okay. And if these intersect each other, then they're going to be non-disjoint. Okay, so high level of satisfaction and more than 5 times per month are disjoint. Non-disjoint. Okay, because they have something in common here, and it might even be better to use the highlighter. So high level, and then we'll use another one here. More than 5 times per month. So we can see the intersection here is 70. Okay, so let's set this up using the non-disjoint rule. The probability of a high level or greater than 5 times per month is going to be the probability of a high level of satisfaction plus the probability greater than 5 times per month minus the intersection of high and 5 times per month, which is 70. Okay, so let's find the probability of a high level of satisfaction. Well, we have 460 of those divided by the total of 700. And then the probability of greater than 5 times per month is going to be 100 divided by 700, and that's here. And then minus the intersection. So remember, the intersection was right here. Okay, so we'll take out the 70 over 700, and we get 490 over 700. Okay, next question says, for a parallel structure of identical components, the system can succeed if at least one of the components succeeds. So let's assume the components fail independently of each other and that each component has 0.15 probability of failure. What is the probability that within a system of 2 components that both fail? Well, since we have independence here, we can just multiply the probabilities together. Okay, so the probability the first one fails times the probability the second one fails is 0.225. Okay, and then part B, what's the probability that a parallel structure with 2 identical components will succeed? And remember, this one we can actually use the tree diagram again. So the first component and the second component. So the first one can either work or fail, and then work or fail. Work or fail. Okay, so the probability that they work is like 0.87. I'm sorry, 0.85. And then the probability that they fail is 0.15. So you can fill all these in, and we can see that the system is going to work when we have at least one working. So this one here, and this one here, okay? So to get the probability that the system works, we can actually take the total probability, which is 1. So once you get the probabilities over here, you're going to get 1. And then you can actually take out this probability here, which is what we're doing. Okay? So we're taking out the probability, and that's where we get that the probability at least one works is equal to 1 minus the probability that none work or both fail. So 1 minus the probability that both fail, which we found right here, gives us the probability that at least one works, which is what you'll get if you add up this probability here plus this probability plus this probability. So here we're using the complement rule. Okay, and then the next part is asking us how many components would be needed so the probability that the system will succeed is greater than 0.9999. So essentially all we have to do here is set up the number of components, just a table. What if we had one component? What's the probability that the system works? If we had two components, the probability the system works would be 1 minus 0.15 squared. Just plugging in the number of components here for n. And then if we had 3 components, this would be the probability. If we had 4 components, this would be the probability. And then if we have 5, we can see this does it right here. And I kept going just a couple of more, but really we can stop right here at 5. So the solution here is that we would need 5 components. Okay. All right, the next question says the head coach of the Phoenix Suns, Alvin Gentry, wants you to tell him the probability of Steve Nash making the winning free throw shot in a game against the Chicago Bulls. Which method of probability would you use to find the probability of Steve Nash making his next free throw? Well, this would be the empirical approach, okay? Because we cannot assume that it is equally likely that Steve Nash would make his next free throw, because there's a whole lot of factors in the game, like does he have an injury, or distractions in the audience and all of those kinds of things, okay? So it would definitely be empirical approach. Remember, classical approach assumes that each outcome is equally likely. Each outcome is equally likely. Now, part B says explain the process that you would use to get the probability of Steve Nash making his next free throw shot by filling in parts 1 and 2 below. The variables x1 to xn can take on the value 0, 1 depending on whether Steve makes a free throw or misses a free throw. So we'll assume 0 if he misses and 1 if he made. Okay. So what does this subscript here? I mean, the question really is, what is this n? What does this mean? Well, n would be the total number of shots that Steve Nash has taken. Okay. And then we would just count up, out of all of these x's here, we would count up the number of ones divided by the total number of shot, and that would be the probability of him making it, okay? And so that's what the second part is. Let the event E be Steve Nash makes his next free throw. Well, if he's taken a total of 3,102 shots, and the number of ones that we counted is 2801, then the numerator would be 2801 and the denominator would be 3102, which would give us a roughly 90% chance that Steve Nash would make his next free throw shot. Okay, next question. All right, so here we have a bag of tulips. We have 30 tulips. And we have 12 red, 10 yellow, and 8 purple. So what's the probability that 2 randomly selected tulip bulbs are both red? And the idea is we're going to do the sampling without replacement. So once we take one out, we're not going to put it back in without replacement. And that makes these two events dependent. So the probability the first one is red and the second one is red is going to be the probability the first one is red, which is here, times the probability the second one is red, given, remember you read this straight line here, given the first one was red. So that's just going to be 12 out of 30 times 11 out of 29, because once we take the first red one out, we only have 11 red left, and a total of 29. Okay, so that's the probability of A. What's the probability the first bulb is red, the second is yellow? So the first one is red, the second one is yellow. Again, this is going to be the probability of getting a red, which is 12 out of 30. Times the probability of getting a yellow. We still have 10 yellow, but we took one out that was red, so we have 29 left. Okay, so this is also equal to 120 over 870. There's an equal sign here. You can put that in. And then we're going to do the reverse. What's the probability of getting a yellow and then a red? Well, there are 10 yellows, so 10 out of 30 times 12 out of 29. Remember, we take one out here. And then what's the probability that one bulb is red and the other is yellow? Well, there's really a couple of ways that this can happen. And so let me show you here everything that can happen. Remember, we select two. So the first one and the second one. So we can either get a red, a yellow, or a purple. A red, yellow, purple, red, yellow, purple, red, yellow, purple. Red, yellow, purple, red, yellow, purple, red, yellow, purple. So how many ways can this happen? How many ways can we get one yellow and one red? Well, we can get one yellow and one red here, and one yellow and one red here. So those are the two probabilities that we found here. First we got the red one and then the yellow. First the red and then the yellow. And then we got the yellow and then the red. Okay, so we're just going to add up these two probabilities. This probability plus this probability. Because these are the probabilities here. This one is 120 over 870, and this one is also 120 over 870. So we just add these two up and we get 240 over 870. Okay, next question. Looks like I got this one in here. Okay, final question. We have a survey that deals with razors and then the rating. So razor A, razor B, and razor C. And then poor, fair, and excellent. So the first thing you want to do is just get the totals. So the total number of razor A's we have is 30. Total number of B is 30. Total number of C is 30. And then also you can see the total number rating poor plus the total number of fair plus the total number of excellent should be the total 90 individuals that we have in the sample. So part A, calculate the probability a randomly selected razor scored excellent. Well, we have 53 excellent, okay, 53 excellent divided by the total 90, okay, so 53 over 90, It's a probability. What about B? Calculate the probability that a randomly selected razor scored poor. Okay, so poor, how many pours did we have? We had 7 of those over the total of 90, 7 out of 90. It's probability. All right, calculate the probability of randomly selecting razor B given the score was fair. So remember, we want to remember the notation, the probability of A given B. Okay, and remember B is what we call the reduced sample space. Okay, so we're going to restrict ourselves only to the fair column. And then out of these 30 individuals, how many of them were razor B? Well, 11. So 11 out of 30. Okay. And then the next part says calculate the probability of receiving an excellent rating given the razor C was selected. Okay. So this is going to be the probability of excellent given C. So remember, we restrict ourselves only to the given category, which was the C razors. So we had 30 of those. And then out of these 30 razors that we called C, how many of them were excellent? Well, 13. So 13 out of 30 is the probability. Okay, happy studying, and I will see you guys on Thursday.